All right, folks. You have a good spring break? Did you go to Florida to mix it up?
Nope, but thank you for the no homework over break at least.
Didn't everyone do that?
I've heard of other undergrad classes that were not, I guess, so.
That's terrible. Vacation should be a vacation. Yeah, Kimberly, I will get back to you about that question you asked me,
Yeah, I can stop by office hours if you want after class, or you can email.
Well, I'm just sort of talking to my group members, about it and stuff. So it's, sorry, it's sort of a process.
No worries.
Okay. Okay, folks, let's see. So today, the topic we're going to discuss is scattering. And so I think it's time to get this show on the road. All right, so I introduced this topic last time doing a one-dimensional analogy, and I'm not going to go back over that, but I will just mention that scattering is the theory of continuum states, and that might not be obvious at first, but it is. So it's sort of the quantum mechanical theory of continuum states. And another way of thinking about it is it's the theory of the states that take you places. I like to think of it as the states that move, and these are the ones that take you places, like a car on the freeway. You can't go anywhere in quantum mechanics without scattering states. And so just to remind ourselves what that is, here's like a box, which is some potential, a localized potential, like an atom, like the nucleus of an atom or whatever. And so it has bound states, right? And you guys know all about that. That's the ground state, E2, E3, etc. But then up here, that's E equals 0, but then above E equals 0, you have your continuum states. Now, those are the ones we care about now, the continuum states. And these are the bound states. Bound states have energy less than 0, and the continuum has energy greater than 0. So just to orient you. And so the basic geometry that we're talking about, the basic scattering geometry is you have some potential, some localized potential, and then we have an incident wave, and then we have the scattered wave. And that's what it is we want to understand, this process, where the scattered wave goes out, say at some energy, some angle theta with respect to the incident wave. And so the incident wave is what goes in, and the scattered wave is what comes out. What comes out. And theta is the scattering angle. And so the basic theory of scattering is sort of like, I got what goes in and I got what comes out, and I want to understand the relationship between these two quantities. I want to understand how I relate what goes in to what comes out. And the thing that's making it all happen, of course, is the potential, the scattering potential. So that's the theory of scattering. That's what we have to understand. So how do we understand this process? Well, let's start with classical, like something that we often do is let's start with classical physics. All right, and so for classical physics, there is a theory of scattering, and that You guys might have learned it, or you might not have, depending on, might have, whether you took the class or it fell between the cracks or whatever. But the classical theory of scattering is this. And understanding the classical theory of scattering is not so important for the quantum mechanics, but I think it's useful. So we have some potential centered at this point, and then we send in a particle. There's my particle, and I'm sending it in with some velocity. But that velocity I think of as an energy. So the energy is, say, 1/2 mv squared. It's coming with some velocity. It's classical, right? And so it has a trajectory, and it just bounces off into some angle. So I can make that a solid line. That's a trajectory. And so and far away, it comes in some distance from this line. So this line goes through the center of the potential, and this is called B, and this thing is called the impact parameter. And this is, what this is important for? This is important for people who like design satellites and space probes. Like you have to really understand this really well if you want to like send a Mars rover thing, to Mars. Then you got to do all this. So people at NASA really understand this. And then this is some angle theta, and so well, that's the scattering angle. But there's and then what you do is the whole point is to get this trajectory. And the way you get the trajectory classically is always just F equals ma, right? That's how you get it. And so, but there's a little bit more. It's sort of like, so you're given the energy of the particle, you're given B, and you're given this. And so that's sort of like what you start with. And to really do the classical theory of scattering, what you want to do, the way you formulate the problem is actually not completely intuitive. There's a sort of, when the first time you see it, it's a little counterintuitive, but it makes sense as time goes on. Like for me, it started making sense about 15 years later. So as time goes on, it will eventually make sense to you. And so here you have some potential. And so the way to think about it is this. It's like we have a particle coming in. Now I got my impact parameter, B, but and then I have the particle coming out. But the way to think about it is this. Draw a sphere surrounding the particle. And then we ask ourselves, and then I have some detector. And the way to think about it is that you want to know, remember, this is what goes in. We have what goes in and we have what comes out. And we want to relate those two things, what comes in and what goes out. And the way we relate it is we ask ourselves, how many particles are going through an annulus here? So this is an annulus, like a donut, not exactly donuts, it's flat. And so it's a ring. It's a ring of radius b, but it has some little width. It has some width, and so it has area d sigma. So that's a little bit of area. And then we have a flux. We have a flux going in. And that flux I'll call L. And it actually has a name. It's called the luminosity. And L is equal to the number of particles it's a flux, so it's particles per area per time. It's like the particles per time per area, because it's a flux. That's always the units of flux, as you guys have heard before. So I have a flux coming in, and then the whole point is that I have this, think of it like this, I have this solid angle, and this is like the iris of your eye, because remember, this circle I drew is a ball, it's a sphere, it's like your eyeball. I think that's the nicest way to think about it. It's like a big eyeball. And so this is the iris of your eye. And so this is some solid angle, d omega equals solid angle. And the best way to think of it is think of this as the solid angle of the detector. Whoops, I just screwed that up. Detector. And so the detector is really covering a solid angle. Detector covers d omega. And so I want to know the number of particles per time goes into the detector. dn equals number of particles per time into the detector. And you want to relate, and here's the crux of the matter, is that the whole essence of scattering is to map the relationship between d sigma and d omega. And that is not obvious, like that's a weirdly sort of weird ass backwards way of looking at things. And so I think the first time you see this, at least I remember as a student, I found it very confusing. Like, for, all of these quantities are not very intuitive. Like you're going d sigma, what the hell is the significance of this little annulus? And now d omega, what's the significance of this solid angle? But as time goes on, it starts kind of making more sense. And this really is the best way to do it after you've thought about it for about 15 or 20 years. And so the idea then is I have this luminosity going in. And so let me now ask you a question. The idea is to understand the relationship. The idea is that we're talking about the particles are coming in, and we want to trace all the particles that hit that d sigma, that go through that d sigma. We want to follow their trajectories, and all of their trajectories go through. We follow their trajectories, and we realize that their trajectories all go through a certain solid angle, d omega. So this d sigma is related to this d sigma is related to this d omega, because all the trajectories that go through the d sigma go through the d omega. And then let's assume that all of those particles go into our detector, which covers d omega, that solid angle. So now I'm going to ask you a question, a quantitative question. I'm going to ask you, how many particles go into the detector in terms of the quantities I've written down? So this is a question to you. How many?
L d sigma.
That's exactly right. That's exactly right. And that is the essence of scattering. If that is the essence of scattering, because that shows you the significance of d sigma, this little weird little annulus at the front, because it's the particles that hit that annulus which are the ones going into the detector. And so that's the relationship that you have to, and that's the simplest way to understand it. All right, although that will come with time. So appreciate that. And so then what we want to do is, if we do that mapping, then there's a really simple way to think of things. Let me also remind you solid angle. I did this last time, a little three-dimensional construction, but I just want to remind you guys what solid angle is. because I know that not everyone is like really super familiar with it. But here's spherical coordinates. This is my r vector. This is my theta in spherical coordinates, right? This is my phi. And let's see, so I have some little bit of area here. And that area, when you go through the spherical stuff, the spherical trigonometry, it's r squared sine theta d theta d phi. You guys have all seen that a bunch of times. And the definition of d omega, a little piece of solid angle, remember it's dimensionless. And so it's going to be dA divided by what? What makes it dimensionless? dA divided by what?
R squared.
That's right. And so d omega is sine theta d theta d phi. I just want you guys to remember what solid angle is. So that's the solid angle. And so then we start with, and so now let's go back to the scattering geometry. And so we have dn is equal to the number of particles per time going into the detector is L times d sigma, right? But to relate it to to relate it to the solid angle, what I can do is, remember, I want to relate the things I want to relate is the d sigma and the d omega. And so what I can do to this little equation, which hopefully this little equation I'm pointing arrows at, hopefully that equation should make sense to you, all right? That's always like the thing you can grab onto, it makes sense. Now let's just divide both sides by d omega. Okay, and so then what I can do then is, whoops. Then what we can do is I can solve, I'm just divided both sides by d omega. And the way to think of it intuitively is that's the solid angle of the detector. That's how you should think of it. And so then what we see is we get this weird quantity, d sigma d omega is equal to 1 over L times dn d sigma, or d omega, sorry. And so now I've defined this, and this is actually, in some sense, the most important equation in scattering. And I've just defined it, so I just sort of pulled it out of a hat, but it's sort of trivial to define it. And this, but it's not very intuitive when you see it for the first time. So this thing has a name. It's called the differential cross-section. Differential cross-section, d sigma d omega, and that is the most important thing. And it's not obvious that it would be when you first see it, but I want you to see what it is. I mean, it's the ratio of that little bit of area at the front end to the solid angle at the back end. So it's really, it is the most important thing because it's the ratio of what goes in to what comes out. D sigma goes in, d omega comes out. So it is the most important thing. And the way that you can sort of see that it's the most important thing is first to notice that these are all the experimental parameters on the right-hand side. Yeah, you have a question? This, because here I have the luminosity, number of particles that go in per time, per area per time. And d omega is the solid angle of the detector. The solid angle subtended by the detector. And dn is the number of particles per time that go into the detector. So look at the right-hand side of that equation. That's basically everything that you know experimentally. That's all the most important experimental quantities. And I've just arranged them in some funky little ratio. And so you can kind of see like, wow, that ratio must be important because it has literally everything that we can possibly measure. and that ratio is the differential cross section. And the differential cross section, when you look at it, is the ratio. Think of it as the, it's the ratio of like the area of the particles going in divided by the solid angle that they come out at. So that's really critical. And so then so this is a definition. So we've defined d sigma d omega, and it's a function actually of theta, the scattering angle. And that also, I remember, is kind of confusing when you first look at it, because when you look at the d sigma, there's no angle there. It's just this weird little annulus. But the angle is defined by what comes out, okay? And think about that, because notice that if I was to pick a smaller d sigma, like let's say I made let's say that I looked at a smaller d sigma, that was where I shrunk that radius of that little d sigma. What would happen, and this is, I haven't defined the angle yet. Let me define the angle. There's the angle theta. What would happen to theta? I'm asking you a question. If I shrunk that d sigma, like made the radius smaller, what would happen to the angle theta? Would it get bigger or smaller? For a repulsive potential. So let's say that say I'm shooting say I'm shooting, what am I shooting? Let's say I'm shooting protons at a nucleus, at some high energy place, shooting protons at like a little nucleus. So it's positive particles going at a positive nucleus. It's repulsive. And now I shrink that d sigma, the radius, I shrink it down. What happens to the scattering angle theta?
Gets bigger?
Yeah, that's exactly right. Because what's happening, if I shrink it down, then I would be following this trajectory. And now it gets pushed harder by that potential. And so it goes bang, right? And if I actually got really close, I would get bounced back. You see that? And so you see that as I change that d sigma, the d omega changes. It starts scattering into different angles. And so that's why the ratio of d sigma and d omega is a function of the angle. That angle is the scattering angle. So I want you guys to try to, to wrap your mind around that. And so then once I make this definition, and I realize these definitions are not intuitive when you first see them, but they are simple. They're not intuitive, but they're simple. But but they're still hard. And so let's define something. Let's take this ratio, the differential cross section, which is a function of theta. And by the way, I've noticed how it's a function of theta, but I'm not including the angle phi. Phi is this sort of azimuthal. Why am I ignoring phi?
It's symmetric.
Right. It has cylindrical symmetry. So it has cylindrical symmetry. So then we can ignore. Okay, so what I can do is I can take this differential cross section d sigma d omega, and now I can integrate it. And I'll integrate it over, guess what? The solid angle. I can do that. It's a quantity, it's a function. I can just integrate it over solid angle. And what is that going to give me? All solid angle. So that means what I'm doing is I'm integrating it like this, from 0 to 2 pi, and from 0 to pi. D sigma, d omega, theta, and d omega, the solid angle, is sine theta, d theta, d phi. And so this is phi integral, and this is my theta integral. Okay, so let's say I do this this integral, what do I get? Does anybody know? Well, first, let me ask you, what are the units of what I get? So even if you don't know what it is we end up with, you could at least figure out the units of it by looking at that equation. What are the units of this?
Should it be area?
Yeah, it's area. You're going to get an area like 1 square centimeter or 10 to the minus 12 square centimeters or 10 to the minus 20 square centimeters. You're going to get an area. What is that area called? Does anybody know? It's called the cross section. That's the cross section of a scattering process. And I think you guys have all heard of that before, that term, cross section. That's the cross section. That's the definition of cross section. So this is sigma, and this is total cross section, the total cross section. And I say total to distinguish it from the differential cross section, right? Because d sigma d omega is the differential cross section. And this is the total cross section. And that is the thing that characterizes a scattering process. So I could say, if I shoot protons at the nucleus of a gold atom, the cross section is 10 to the minus 22 square centimeters. That's a number. That is, and so scattering processes are characterized by an area. And it has units. Does anybody know what the units that they, like high energy people have like a unit that they use? Do you know what the name of the unit is? It's called a barn, because it's like hit the side of a barn, get it? Ha ha ha. High energy guys have a good sense of humor. Barn. Seriously, that's why they call it that. It's some tiny number. I can't remember what it is.
So, sorry, what is the phrase?
Barn, like you can't hit the side of a barn. Have you heard that term before? Like it's a
Can't hit this. Oh, okay. Sorry, I get it now. Thanks.
like an American colloquial saying, like, oh, you couldn't hit the side of a barn. Barn. So the units of cross section is barn. Okay, so but I just want you, when you first see this, it's kind of strange because you're thinking, why would I characterize a scattering process with an area? It sort of makes no sense. But it does make sense when you think about it, because the point is that if I'm shooting particles at this potential, then the particles are bouncing off into some solid angle. And so the point is, if I start with an impact parameter of 0 and I start increase, and if I start with an impact parameter of 0, what is my theta? Tell me. Impact parameter of 0, what's theta?
Pi.
Exactly, it'll bounce back for a repulsive scatterer. And so then as I start increasing that impact parameter, the particles start scattering into smaller and smaller angles. And at some point, I'm going to increase that radius, and the theta, the angle will be what? It will start for impact parameter 0, the angle is pi, but at some radius, the theta will go to what? Tell me.
0, like it's not gonna deflect at all.
Exactly. And that then is the area of your scattering process. Do you see? It's like, at what point does that angle go to 0? And that maximum distance defines an area. And that is the area that defines your scatterer. And that's it. That's the way to think about it. And the way to think about it is like that. What that means is that the scatterer is gonna, that means that if I'm sending a luminosity, a flux of particles at the scatterer is gonna scatter all the particles within that area. That's like the footprint of the particle, of the scatterer. And so that's what the cross section is. It's like the footprint of the scatterer, because those are the particles that are going to get knocked out of the beam. The beam comes, and only the ones within that cross section are going to get scattered. All the other ones are just going to keep on going straight. You see? So it's actually a very natural unit. It's very natural to define a scattering process in terms of area. But it takes a while to sort of see that. You have to think it through. Okay, so let's keep going. Now what we're going to do is let's talk about quantum mechanics. The quantum mechanical theory of scattering. Because we haven't even done any quantum yet. That's all classical. Hold on one second. Okay, so let's do that. So for the quantum, so that was the classical theory of scattering. Now let's do the quantum mechanical theory of scattering. So for the quantum mechanical theory of scattering, what we're going to do basically is wherever you see the word particle, replace it with the word probability. Probability. That's the key. And really, seriously, so if you do that, then it all becomes sort of simple. So let's do that. So let's see if we can do this without making it too complicated. So let's do classical on the left. Classical, and now on the right we'll do quantum. So here we'll do this. We have some potential V of R. I put a sphere around it like the eyeball. I shoot a particle in, it gets deflected out, and there's some solid angle, like the iris of your eye, that's d omega, and it goes into a detector that covers that d omega, but then I have dn equals the number of particles per time that go into the detector, right? That's the detector. And then, you know, the detector is covering the solid angle, so it's sort of like a funky, weird detector, but people actually build them like that. And then I have my luminosity, which is incident. And my luminosity is number of particles per time per area, because that's the units of flux. Okay, and so then with that definition, then it's very natural and simple to see that I can define the ratio of the little area that they come through, that little area, d sigma, and that ratio of that area to the solid angle is going to be 1 over the luminosity times dn d omega. Okay, and the detector covers the solid angle d omega. Okay, so that's classical theory of scattering. And so now let's do the quantum mechanical theory of scattering. Same thing. I got the same potential. And I'm going to put a sphere around it. And now, but now it's quantum mechanics. And so instead of, so in quantum mechanics, there are no trajectories. So really trajectories don't exist in quantum mechanics. I mean, you could sort of create a wave packet and have it follow a trajectory, but it's sort of artificial. Quantum mechanics hates trajectories. And so basically what we have then is instead of a instead of an incident particle, there's my little particle following a trajectory. Can you guess? The particle is following a what? What is the particle following? Can you guess?
Like a probability distribution.
Yeah, but like a free particle moving in some direction? How do I describe that in quantum mechanics? What's the simplest way to describe a free particle moving in some direction?
Like a wave packet.
Even simpler than a wave packet. That's actually pretty hard. What's even simpler than a wave packet?
Just a wave.
Yes, a plane wave, a single plane wave. That's right. And so I send a plane wave in. And so that wave, that was a pretty lousy wave, but whatever, it's the best I could do. So that's, and it has some momentum incident, K incident. And it's a wave, and it's a plane wave. So I'll call it the incident wave function, psi I for incident, and it's a wave, e to the I, k I dot r. That's the incident wave function. It's just a wave coming in at the potential. But now to make the math work, the easiest way to make the math work is to put everything into a big box and normalize it, because we got to keep track of all our normalization. And to be quite honest, it's sort of tricky. The math can be tricky for continuum states. But if you just put everything into a big box, if you just say the universe is in a box, then the math becomes much simpler. So let's do that. So we'll put the universe into a box. Size of the universe is L on the side. And that means that the normalization factor is 1 over L to the 3/2. And you can see that, just square that wave function, integrate it over the box, and you get 1. Okay, so then I have some final, then it scatters off of that potential, and I have a wave that goes out. And that wave that goes out, let's see, that wave goes out and it hits a detector, and there's a solid angle. So these definitions are the same. Like the iris of your eye, that's d omega. The detector is also covering d omega, the same solid angle. That's the detector. And and now I have the final wave function is coming out with some final momentum, which is going in that direction. This wave function then is the final wave function, and it's normalized, and it has momentum in the direction of the final momentum. Okay, because that's what goes in and what comes out. All right. So I have a plane wave comes in and a plane wave comes out and it goes into the direction of that detector, where that's the angle. No, this is the angle theta. Same angle theta. It's all the same. Okay, but now we got to start mapping these quantities. So remember, on the left I have L, right? On the left I had L is equal to number of particles per time per area. But now I want to convert that into quantum mechanics, because in quantum mechanics it's not classical. So what is the quantity that's important that I replace? What do I replace L, the luminosity, with? What do I replace it with? I replace it with something. What do I replace it with?
A flux.
What flux?
I think probably just the probability flux.
I'm sorry, say it more clearly. The what flux?
The probability flux.
That's exactly right. Because you just, that's right. It's so simple. That's very, very good. Oh, whoops. Very good, because what we're doing is you're just replacing the word particle with the word probability. That's all. So we're going to replace it with probability per time per area. And that's the probability flux. And what is the symbol that we've been using for probability flux in this class and also in your class last semester?
J.
Say it again.
J.
Yes, that's exactly right. And so I'll call it J incident. And we'll take the magnitude of it because it's actually a vector, right? And so we'll take the magnitude of it. Let's see, can I erase this from the screen? Yeah. That's right. So L goes to J incident. The incident probability flux equals probability flux. And that makes sense because classically we had particle flux, you know, we're shooting BBs, you know, at a thing and we're following the trajectory of every single BB. But now in quantum mechanics, we're shooting a wave at the thing. It's a wave, a probability wave. And so it has a probability flux. Okay, good. So let's keep going. And so we know that, you know, the most important thing in scattering, as I said, is the differential cross-section, d sigma d omega. So let's figure out what that is in quantum mechanics. And so, because in quantum mechanics, it's the same thing. The d sigma d omega is the most important thing, and it's a function of angle of theta. And classically, it's 1 over L. And so here, I'm going to replace the L with the J, right? The incident J. But then now I have the dn. And remember the dn is number of particles per time. And I have just d omega, that's just solid angle. So the part on the bottom stays the same because solid angle is solid angle. Whether it's classical or quantum mechanics, it's still just solid angle. But the dn is different because for the classical theory of scattering, I have number of particles per time. But for quantum mechanical scattering, I'm shooting in a wave and the wave is scattered. And so it's all probability that's flowing. So forget about these trajectories. There are no trajectories in quantum mechanics. I mean, you can make one, but it's bogus and sort of artificial. Quantum mechanics hates trajectories. So what do I replace dn with? Somebody tell me. dn equals particles, the number of particles per time. And I'm going to replace that with what?
No, probability per time.
Yes. That's right. And that should make perfect sense because it's probability. Because remember, we've already talked about probability in this way. Probability is stuff. Probability is conserved. You can't just create lots of probability. It goes places. The probability used to be flowing in on the left, but then so think of it as water. So the incident wave is like probability water. It's flowing like the green goo that we talked about when we did time-dependent perturbation theory. It's the same stuff. So the probability amplitude is flowing from the left, and then it splashes, it hits the rock. It's like a stream. The stream is flowing, it hits a rock, and then the water scatters from the rock. It splashes. So it's like liquid. That's how you should think of it. And so it's probability per time. And that probability flows into the detector, and the detector captures the probability. Now, we encountered this concept of probability per time before. And what did we call it? What did we call it? We gave it a name. I'll give you a hint. It was in our discussion of Fermi's golden rule.
Wasn't it just the rate or the probability rate?
That's right. It's the same thing. It's a rate. It's a transition rate, probability per time. Because the way to think about it is that the particles flowing has some probability to be going forward, and then it has a probability to scatter. And some of the probability scatters into the detector, and the detector's capturing it. And it's probability per time flowing into the detector. Probability per time is rate. That's the rate of transitions. That's the number, that will eventually give you the number of particles per time that the detector's capturing. but it's probability per time, because in quantum mechanics, we can only calculate probability. So we'll use the word R. Now, R is for rate, but it's only, I call it dr because the detector is only covering d omega, a differential solid angle, and so it's just capturing a small part of the probability fluid. If I integrate over the whole sphere, then that would be the total rate, which corresponds then to the total cross section. Okay, so dr. So then what goes? So then on top here, instead of dn, I'll put dr. Make that R a little better. And so this is probability per time. And so that's the quantum mechanical theory of scattering. We got it. We have the differential cross section, because the differential cross section is the most important thing, because remember, you know, the total cross section sigma is the integral of the differential cross section. And so once we have this, that's the most important thing. And so now we have it in quantum mechanics. We have it. We see that the differential cross section for a scattering process is equal to 1 over the incident probability flux times the rate, the probability per time that goes in, the probability per time that flows into the detector, which is covering d omega. So there's a relationship between what's on top and what's on bottom. They're not unrelated, there's a relationship. And so this is the differential cross section in quantum mechanics. So let's calculate that. So let's find it. And you see, to find it, we need two things. We need the probability flux, the incident probability flux, and we need this weird quantity, dr, d omega. Okay, so let's get those things. Let's find them. And so let's find it. And so let's start with J incident. That's the easy one. J incident. That's the one that's easy. So we go back to our little picture and we see that our incident wave function, it's the incident wave function that gives us J incident. And there it is. So the incident wave function is psi I, it's a function of R, is equal to 1 over the size of the universe times the momentum. That's the wave function. And so to find J incident, and remember this is in 3 dimensions, so J is a vector, it's a flux. How do I find it? Somebody tell me. It's a little formula. Does anybody remember the little formula? Anybody remember it?
H bar over 2mi psi conjugate partial psi partial r cubed, I guess, in 3 dimensions.
Yes, psi star del psi minus psi del psi star. It's this weird formula. Pretty easy to derive, actually. You guys derived it last semester, and it's you know, there's a very straightforward way to derive it. But the formula itself is weird looking and not intuitive. And you probably thought it was, you know, and you probably thought you'd never have to see it again. But here it is, suddenly coming back. It turns out that this formula is shockingly, surprisingly important. This is the flux, the probability flux. This is the fluid. It's flowing. So that wave function is a continuum state psi, and it's describing a flow of probability. That because the particle is moving in that wave function. You know, this is a plane wave, but the particle is moving. Particle is moving. And so you might ask yourself, how do I think of the particle moving in that plane wave? Well, the real way to think about it is the probability fluid. That's really how you think of the motion of the particle. It's because you guys are all stuck on trajectories. Forget about trajectories. It's all probability, and the motion of the particle is the flow of the probability. And this is really important. For example, if you make a tiny device, if you want to make the smallest computer in the world and you want to make little tiny electrical circuits, then these wires are now starting to become on the size of you know, the wave function. The quantum mechanical properties now are becoming important as you start making electrical devices. And so now if you're an electrical engineer and you're starting to design circuits, you know, at these tiny single nanometer length scales, then when you start talking about the electrical current that flows through a tiny circuit, how do you visualize and calculate as an electrical engineer the flow of current through a tiny circuit? Well, what is flowing? What is the electrical current that's flowing in a computer at these small length scales? What's flowing is probability. The electrical current flowing through the circuit is actually a probability current. And so there's a one-to-one matching of electrical current and probability current. So in the modern theory of electrical current flow in tiny structures, what you're following is the probability current. And so this probability current is not just some abstract thing for this class. It's how you design computers. Okay, you know, it's like how you design the computers of tomorrow. You know, the electrical current is the probability current. There's a one-to-one matching. And so that's so it's actually very practical and important. Okay, so let's calculate it. So now we just have, so we see that psi star. Oh, and by the way, that thing about electrical current equals probability current, that's called the Landauer theory. Maybe you've never heard of it, but that's the Landauer theory of electrical conductivity. That's the modern theory of electrical conductivity. Okay, psi star then is going to be 1 over L to the 3/2 e to the minus I ki dot r, because the formula tells me to take the complex conjugate, and then I have to do del psi. And the nice thing about plane waves is that we love plane waves because when I take a del of a psi, what does the del turn into? Oh, it's plus. Oh no, that's nice. Yeah. What's del? What does the del turn into? I have a plane wave and I'm doing del on the plane wave. What does the del turn into? What does the del turn into? We love plane waves. This is the whole point. This is why we love plane waves. This is it right now, at this moment. This is it. Why do we love plane waves?
Second order spatial derivative.
Well, del, if it was the wave equation, we would be taking the second derivative, but it's not the wave equation yet. So it's just one derivative, del. So what does the del turn into when I take that derivative?
D
Oh.
by r.
Yes, that's right. It's the del operator, and you can look in your book, you know, in some complicated formula in spherical coordinates, and it's easier in Cartesian coordinates. It's really simple, but I'm asking you, what does it turn into? Do the math. I'm asking you to actually do it. Take the del, the gradient of a plane wave, and tell me what it is. Do the math in your head. Take all the derivatives and do all the vector calculus in your head right now, this moment, and tell me the answer.
Just a constant times psi, right?
Yeah, but what is that constant?
IK.
That's right. IK. Del becomes IK. E to the I K dot R. That's right. That's why we love them. The del turned into an IK. And what if I had done, here's another question. What if I had done the time derivative? Oh no, actually, wait, I don't have a time derivative. Never mind. We won't do the time derivative, but okay. And I know you guys have all seen this before. The del just turns into an IK. That's why we love it. The math is so simple. Okay, so now we do all the math, and what we get, I'm not going to do the math. That's all the math that I'm going to do. for that. But now let's continue forward. And so if you do all the math, then what you get is this. You're going to get that and it's easy, okay? You know, plug in the things, multiply everything out. You guys do it. And when you do it, then you get this. H bar K incident divided by ML cubed. Very simple formula. And so that's the incident probability flux. and it really does make sense as a probability flux, because it's kind of like, you guys remember flux, sort of like, you know, this is just an aside, but you know, flux, you guys have seen flux before, like current flux. Flux is always a density times a velocity. Density times a velocity. That's what flux always is. And you learned this at some point, so it should look familiar to you. But now we have a probability density, because what is flowing? It's probability. But flux could be anything. You know, you could have a flux of cats per volume times velocity. They're flying at you. Someone's throwing cats at you. You could have a flux of frogs. They're falling from the sky. And so there's a flux of frogs falling from the sky. You have frogs per volume times the velocity of the frogs as they hit you on the head. So you could have a flux of anything, but now we have a flux of probability. And so the density of probability is 1 per what? Probability is conserved. I have probability 1 per what? Per what volume? It's a density. What is the density of probability? It's 1 per what?
Okay.
No, that's a good guess, but at least you tried. But no, because it has to be a volume. It's probability per volume. Density is always stuff per volume. What? So it's 1 per what?
Like meter squared or something?
Say it again.
Meter cubed or something like that.
Well, that's the units. That's the units. But I'm not asking for the units. I'm asking for the actual magnitude number. Probability is 1 per what volume? I'm asking for, I'm asking for the actual amount of, the density. Density is like a specific amount of stuff per a specific volume. That's how you calculate density. So if yeah?
For volume of the universe, there's
Yes.
1 of this universe.
And the universe is what? What's the volume of the universe?
L cubed.
Yes. Thank you. And now the velocity. Well, velocity is momentum over mass in the simplest way of thinking. And momentum is h bar k divided by mass. So now look at my little formula here on the left. H bar k over ml cubed. I just want you to see that this formula you end up with is very sensible. It's very intuitive. It makes perfect sense. It's a density times a velocity, flux, probability flux. Okay, so okay, that was the easy part. Now let's do the hard part. So the hard part is to calculate this. So that was the easy part. But now the hard part is this thing, dr. dr is probability per time. And that's what we have to calculate now. So this is the geometry, this picture on the right. A plane wave goes in and it scatters and comes out. And we need to calculate the rate at which the probability scatters. It's like I have the particle is in a state, an initial state, and then it scatters to a final state. And I need to know the rate of those transitions. So does this sound familiar? How are we going to calculate that rate? And we're going to use something that we learned in class. What are we going to use? Somebody tell me.
Can we use Fermi's golden rule or no?
Yes, we will use Fermi's golden rule. Very good. That's good. Yeah, that's exactly right. And the reason why we use Fermi's golden rule, already here, golden rule. The reason we use Fermi's golden rule is because we're starting in one state, which is the initial state, and we're scattering into the final state. But the final state that we're scattering into, it's not just one state, because there's many states. So the way to think about it is like, here's the scatterer, the potential, and here's the initial state. I represent it with an arrow, the initial momentum. But notice that when I scatter, I could be scattering here or here or here. Do you see what I'm saying? All the possible final states is all these arrows. These are all possible final states. And so if I was to draw that, it would be a porcupine. So that's how I want you to think of it. It's a porcupine, you know, like the little animal with the little needles sticking off all around it. Because there's like little arrows pointing everywhere, like a sea urchin or a porcupine. You grab it and they poke into your hand, and it hurts. It hurts a lot, but you do it anyways because it feels good. So you grab it, all right? So picture it, you know, all these needles sticking out in every direction, all the possible final KFs. But the thing is that the detector is here. That's your detector covering some solid angle. So notice that there's not just one arrow going into your detector, there's sort of a whole bunch of them. Do you see what I'm saying? And so the point is, and this is not intuitive when you first see it, but after you think about it, you realize, okay, that makes sense. What we have is a dense set of final states. And the reason is because it's a continuum. And so this is exactly Fermi's golden rule. We have one initial state, and we have a dense set of final states. And when we derived Fermi's golden rule, we did it for this. We had one initial state, and we did it like this. We sent h bar omega at it, and we went to the dense set of final states here, right? Because we had a sinusoidal perturbation, but now we don't have a sinusoidal perturbation. This was what we did before. Before we had a sine omega t perturbation. Maybe I'll make it more clear. Before we had h prime equals h naught sine omega t, but now what we have is initial, final, and this is v of r. We have h prime, the perturbation, is equal to v of r. It's constant. So before we had this, where we had the h prime is 0, then at t equals 0, it turns on and it does this. It oscillates as time goes on. But now, the situation is like this. We have h prime. This is at t equals 0. It turns on, and it just stays on. It's constant in time. It's just the potential v of r. Okay, so this is the situation. So this is the way you should think about it. It's sort of like, the way to think about it is, we have the initial state. It's a plane wave. The plane wave has just been flowing since the beginning of the universe. All right, there's no time in a plane wave. It's just flowing, and then And then at t equals 0, we turn on the potential. Boop, it turns on. And then suddenly the probability fluid, it used to be just a river. There were no rocks in the river, just flowing since the birth of the universe. Then at t equals 0, we throw a rock into the river. And now the water starts scattering off of the rock and it starts spraying in all directions. And we want to know how much of that water is spraying in one particular direction. But that particular direction is actually a dense set of directions. Okay, so that's the picture you should have in your mind. Okay, so we use Fermi's golden rule. And so Fermi's golden rule then for this situation is this. We'll use the form of Fermi's golden rule that we derived, but it looks a little different because we don't have the sinusoidal perturbation, so it's different by a factor of 4. I actually mentioned this in class, you might not remember, but if you derive we derived Fermi's golden rule for the sinusoidal potential, we got a formula. I think what we derived was R. I'll just write the formula that we derived. We derived R equals pi over 2h bar times the matrix element that connects the initial and the final state. Actually, I'll write it like the way we derived it. H prime times the density of states. Okay, and so that was the matrix element. And that's the density of states, DOS. The density of states for the final states. But now, so this was before, but now we have a different situation because it's this constant perturbation that just turns on. There's no sinusoidal. And so when you go through all the math, and I'm not going to go through all the math, but it's not hard to do. It's just the same math we already did, but without the sine omega t. When you go through the math, you have R equals 2 pi over h bar, just different by a factor of 4. And the matrix element is now the potential, right? The potential V of R, and I have the final state and the initial state. And the density of states is the density of states going into the final, into that d omega. And so it's d rho of at the final energy. Well, I should just say the energy of for scattering, there's only one energy. Energy is conserved because I just want you to say, like, energy here, the energy going in is kinetic energy, h bar squared k squared over 2m. Energy initial and energy final is also h bar squared k squared over 2m. Because the energy is conserved, it's just the direction of the particle that has changed. So we're only talking about elastic scattering. Elastic scattering. And elastic scattering means that energy is conserved. So that should be intuitive, because what goes in comes up. So because the scatterer is not absorbing any of the energy, it's just bouncing you. And so, but because we're only talking about the scattering into one particular dense set of final states, that means this is dr, because it's the rate that goes into that one direction. Okay, so that's, and here, oh, I got a little squared there. And of course, the definition of that matrix element is the same definition. It's just the matrix element where I have the final state, I have the perturbation, which is the potential, and the initial state. Okay, that's how we use Fermi's golden rule in the context of scattering. But now let's keep going. So let's write out what that VFI is. So VFI is a matrix element, so it's an integral. It's an integral over what variable? Somebody tell me.
Isn't it R?
Exactly. Volume. So it's all volume in the universe. So it's an integral over d cubed r in spherical coordinates. And then I have on the left, I have the final state, which is what? Somebody tell me. There's three parts to this. What's the first part of this integral? Tell me. What
So
is
it's
it?
the normalization constant and then e to the negative I kf dot r.
Exactly. That's exactly right. Because on the left-hand side, so it's complex conjugate. That's exactly right. Okay, what goes here in the middle? What goes in the middle? What goes in the middle?
R.
Say it again.
V of R.
Exactly. Perfect. It's the potential. That's exactly right. And what goes here? What goes there?
1 over L, 3 halves times e to the I k I r.
Exactly. Perfect. That's exactly right. Initial state. We're using Fermi's golden rule. We have an initial state and a final state, and it's telling us how things scatter. That's exactly right. So that's the matrix element, okay? So you got to do that integral. And it's a well-defined integral. You just do it, all right? So, okay, so that part is done. So we got that, but now the only part that we don't have, and I'm gonna rewrite that. This is equal to, I'm gonna pull the L's out. It's equal to 1 over 3 halves plus 3 halves is 1 over L cubed, right? I always get these out screwed up. Yeah, L 3 halves times 3 halves is 3 halves plus 3 halves. It's 6 halves is L cubed. Yeah, okay. 1 over L cubed times the integral of e to the minus I kf dot r v of r e to the I k initial dot r d cubed r. And there's even another way to think about it, which is kind of cute. Let's do it like that. VFI is equal to 1 over L cubed times the integral over volume times e to the I e to the minus I k final minus k initial dot r v of r. Okay, that is the matrix element. And this is going to turn out to be really important because notice that this is delta k, the change in momentum. That's the change in momentum due from the scattering, Eli. Change in momentum. Change in momentum. The particle changes its momentum, and that momentum change is in that integral. Okay, that turns out to be really important. Okay, now we got to do the next part. We got to find this d rho. D rho EF equals what? The density of final states. So we got to do this. So remember, we have our initial state, and then we have our porcupine, and we have our detector d omega, And so we got to basically figure out how many states are going into that d omega. Okay, so d rho, the d rho is the density of final states going into the detector. And so that's going to equal the total states per energy. That means the whole porcupine times a fraction. It's going to be d omega divided by what? Can you guess?
Four pi.
Yes, exactly. Because the total solid angle of a sphere is 4 pi. And the detector is only covering a fraction of that, d omega over 4 pi. And so the density of states, or the final states, is the total density of states times a fraction of those states going into the detector. Okay, so then the question becomes, what is the total density of states? Okay, so now we have to find the total density of states of that porcupine at a particular energy. So what is the total density of states? So let's calculate it. Now, I've already done this for you before in 1D. So we have to calculate now the 3-dimensional density of states. And I'm assuming that all of you have actually seen this before. Probably most of you have seen it in some classes, like in in 7C, but some of you might not have seen it. So I showed you the 1-dimensional density of states calculation. Now I will show you the 3-dimensional, and I often put the 2-dimensional on the final, just so you know. Let's see. So density of states. So the point is this. Let's do this. Let's calculate the 3-dimensional density of states. This is the way to remember it. And this is the same as the 1-dimensional, but just a little bit more math. So this is the thing. We have E versus K. This was the picture I drew last time. And there's the states in K are quantized. And you guys remember how they're quantized? It was because I could do, if this was X and there's a box at L, then I have periodic boundary conditions. And so that means that L is equal to n lambda. And so K is equal to 2 pi over lambda is equal to, so lambda is equal to L over n. So it's 2 pi over L times n. Okay, so K is quantized. That's the basic quantization of K, 2 pi over L times n. And so the little unit of K is 2 pi over L. All right, and so then what we do then is we say, okay, if we take a little range of K, dk, then we look at those states, and then they translate into a range of energy, dE. And my favorite way, there's many ways of deriving density of states. This is my favorite. My favorite is to say that the total number of states on that energy interval is rho of E dE. But then the total number of states, if I look at it from the K perspective, is the density of states in K space times dk, where the density of states in K space, d of k, is equal to the number of states per delta k. But I know that the number of states per delta k is 1 per what? 1 per what? What's the density of states in K space? Well, we're actually running out of time, so I'll remind you, it's this thing right here. 1 per 2 pi over L. That's the delta K per state. And so the density of states is the inverse of that, L over 2 pi. So this is just in 1D, this is just L over 2 pi. And then remember, we would then say rho of E is equal to then L over 2 pi dk dE, right? Which is equal to L over 2 pi dE dk inverse, where E is equal to h bar squared k squared over 2m. So we did this in class, but now I'm going to do it in 3D. In 3D, it's a little different because now what happens is we have, instead of just one line, we have a volume of K. We have Kx, Ky, oops, Kx, Ky, Kz. And so we have quantization in all three directions. And so really, you should think now of K as a three-dimensional grid. I can't draw it, it's too many dots, but I have a three-dimensional grid of dots. And so now for the energy, I have a sphere. And so there's a shell. So dE corresponds to a spherical shell in K space, spherical shell of states in K space. And so the way to deal with that spherical shell is to say this, is to say that rho E dE is equal to the density of states in 3 dimensions times the volume of K space occupied by those states. But this volume is equal to a spherical shell. And that spherical shell has a volume, it's a spherical shell, and we're running out of time, so I'll just tell you what it is. It's 4 pi k squared dk, because that is the volume of a spherical shell, because that 4 pi k squared is the volume of, is the surface area of a surface area of sphere. And so it's the surface area times the thickness, right? Where that's dk and that's k, where energy is equal to h bar squared k squared over 2m. And so then we have rho of E dE is equal to, and then the density of states in K space is just going to be that same thing as in 1 dimension, L over 2 pi, but now it's cubed. And d cubed K is going to be 4 pi K squared dK. So now we have rho of E is equal to L over 2 pi cubed times 4 pi K squared dK dE. And that is the three-dimensional density of states. And this is dE dK inverse, where E is equal to h bar squared k squared over 2m. And so just plug it all in, and then I need you to do this at home. And what you're going to get is the final answer that you will get when you plug it all in, is you're going to see that rho of E is equal to ml cubed times k over 2 pi squared h bar squared. Okay, so that's what you will get. where K, of course, is equal to the square root of 2me over h bar from this. Okay, so that's the density of states in 3 dimensions. And so then you see that the d rho EF that goes into our formula is going to be rho of E times d omega over 4 pi. So I just multiply that by d omega over 4 pi. So that's then going to be 8 pi, 2 pi, yeah, okay, times, okay, so then it's going to be ml cubed k over 8 pi cubed h bar squared times d omega. So that's it. And then I just want to sort of finish what we had, because we remember we had that dr, the whole thing that we were trying to calculate is 2 from Fermi's golden rule is 2 pi over h bar times that matrix element squared times, remember it was d rho, and so this part goes here and the matrix element goes there, matrix element, which we calculated, and so we put it all together, and we see that we have dr is equal to 2 pi over h bar squared, 2 pi over h bar times that matrix element k final d of r k initial squared. Now we have m l cubed k over 8 pi cubed h bar squared d omega, and we pull this d omega underneath, and so then we end up with dr over d omega is equal to ml cubed k over, I realize that some of you have to go. It's okay, you can just look at the video, but I just want to finish the derivation. 4 pi squared h bar cubed times this thing, it's going to be 1 over L to 3 halves e to the minus I k final dot r v of r e to times 1 over L to 3 halves e to the I k initial dot r squared, and that's going to end up with then it's going to end up giving you m k over 4 pi squared h bar cubed times L cubed times this matrix element k final over v k initial, where this is equal to squared, where this is equal to the integral of e to the minus I k final dot r v of r e to the I k initial dot r e cubed r. And so then we have the final thing is our differential cross section d sigma d omega is 1 over j incident times dr d omega, and when we plug it all in, we get ml cubed over h bar k times mk over 4 pi squared h bar cubed L cubed times k final v k initial squared, and a bunch of stuff cancels, and you end up with d sigma d omega is equal to m squared the L's cancel, most importantly. The size of the universe does not come into play. 4 pi squared h bar to the 4th times the final, the matrix element connecting the initial and the final states. And so this is the Born approximation. Oh, and I went over, I'm really sorry for going so far over, but I just wanted to finish that derivation. Okay,
Professor.
folks. Bye-bye. Yeah?
There was a squiggly sign like above the KF and KI.
The reason I did it is because I did it like this. The reason, yeah, I'm sorry for pulling that on you. I'll show you. Because this is equal to the integral e to the negative I kf dot r v of r e to the I k initial dot r d cubed r. And what I've done is the size of the universe it's basically it's the matrix element that you would get if the size of the universe was normalized to 1. See what I'm saying? That because I just pulled the L out.
I see. Thanks.
Okay. All right. Okay. Bye-bye.